Hello, my name is Piotr Skowron and this is my joint work with Dominik. In our work, we are dealing with a model for approval-based committee elections. In this model, we are given a set of candidates and a set of voters, and the voters express their preferences by approving subsets of candidates. For example, in here, voter V1 approves 4 candidates, the green, the red, the orange, and the pink one. Voter V2 approves 3 candidates, voter V3 approves 4 candidates, and the remaining 2 voters approve 2 candidates each. An approval-based committee election rule takes this kind of a preference profile as an input and a desired size of the committee to be elected. Through this talk, I will use the symbol K to denote the size of the committee. So an approval-based committee election rule takes an approval-based preference profile and K, the desired size of the committee to be elected, and returns a K element subset of the set of candidates. Let's look at this preference profile with 8 voters and 9 candidates, and I will represent these kind of preference profiles also through these box diagrams. In these box diagrams, the candidates will be represented by boxes, and the idea is that the candidate is approved by all those voters that are below the box that corresponds to a given candidate. So let's look at this example, and let's assume that our goal is to select K equal 4 committee members. Which committee would be good? Which committee would be proportional, that is fair to the voters? In this particular example, we can see that we can divide the set of voters and the set of candidates into these joint groups such that the voters from a single group all approve the same candidates, and these candidates are not approved by any members of other groups of voters. In this particular example, it is quite easy to identify a committee that is good. It seems intuitive that we should select 2 members from the first group of candidates, 1 candidate from the second group, and 1 candidate from the third group. Indeed, if we do so, then the number of candidates selected from each group would be proportional to the size of the voters who approve this group of candidates. So in this example, identifying a good proportional committee was easy, but this was due to a very specific structure of these preferences of the voters. In particular, any approval sets of any 2 voters were either the same or disjoint. However, what happens if the preferences of the voters can arbitrarily overlap? In this general example, identifying a proportional committee is no longer easy. Indeed, if we try to plot this box diagram that corresponds to this approval-based preference profile, then it is no longer so nicely aligned. So how could we identify a proportional committee in this example? What does it mean that the committee is proportional? This is the central question of our paper. But in order to answer this question, let's first move back to the end of the 19th century to Scandinavia. There, 2 Scandinavian mathematicians, Thiele and Phragmén, were involved in a somehow heated discussion about what is a good approval-based committee election rule. Each of these 2 mathematicians came up with a very nice proposal. Let's first look at the approval-based committee election rule that was proposed by Thiele. This rule currently is known under the name of proportional approval voting, and it works as follows. We traverse through all K element subsets of candidates, through all committees, and for each such a committee, we compute its score. The tricky part is how the score of a given committee is computed. So let's assume that we have a committee W at hand, and we want to compute its score. Assume that the voter V approves T members of this committee W. Then such a voter assigns the following score to this committee. It equals 1 plus 1 over 2 plus 1 over 3, and so on up to 1 over t. So let's look how does it work for our example. Assume that this is the committee that we want to compute the score of. We observe that the first voter approves 2 members of this committee, namely the green and the red one. So this voter assigns the score of 1 plus 1 over 2 to this committee. Similarly, voter V2 approves 2 members of this committee, so she assigns exactly the same score to this committee. Voter V3 approves all 3 members of this committee, so she assigns the score of 1 plus half plus 1/3, and so on and so forth. So the score of the committee is the sum of the scores that were assigned to this committee by all the voters. So we traverse through all the committees, we compute these scores, the scores of these committees, using this scheme of harmonic numbers, and we pick the committees with the highest scores. And this is how proportional approval voting rule works. For the Phragmén's rule, there are several alternative definitions. We'll use here the one which is based on the concept of money. Here we assume that the voters earn money with the constant speed of $1 per time unit, and we also assume that buying a single candidate requires n dollars. Thus, in the first moment, when there is a group of voters S who all have n dollars in total and who all approve a not yet selected candidate, the rule stops and does the following. It adds C to the committee, and it makes voters from S pay for C by resetting their budgets to 0. Clearly, the remaining voters, those who do not approve C, keep their money in their pockets. So let's look at how this rule behaves on this example. Here, the number of committee members to be elected equals 12, and the rule starts at time equals 0. At this time, no voter has any money. In time 2, the first 3 voters, each of them earns $2. So in total, they have $6. This is enough to buy a candidate that they approve of. So the rule selects one of these candidates, for instance, C1, makes those voters pay for them, and resumes. Next, in time 4, those 3 voters, managed to once again collect $2 each. They in total have $6. That is enough to buy another candidate, say C2. In time C6, those 3 voters again can buy another candidate, namely C3. But also here, in this moment, V4, voter V4, managed to earn $6, which is enough to buy a candidate that only this voter approves. So, for example, C7 will be selected. Similarly, V5 has enough money to buy a candidate she approves of, that is C8, and C9 will be also selected. Next, in time 12, if each of the voters can collect $6, so each of them can buy a single candidate that she approves of. After such a purchase, 12 candidates are selected, so the rule stops, and these candidates shaded in the left picture are those which will be selected by the Phragmén rule. This is a very intriguing question. Initially, both Thiele and Phragmén argued that their rules are proportional, and the arguments that they used were based on the fact that these rules behave well on well-behaved profiles. For example, for profiles where the approval sets of any 2 voters are either the same or disjoint, that is, the profiles with this very nice structure that I started my presentation with, for these profiles, both of these rules will behave as expected. Historically, PEV was preferred since it appeared simpler, and current research suggests that PEV is superior in terms of proportionality. Several arguments in favor of PEV were formulated, and here I want to briefly recall one of these arguments. Let's look once again at our example and recall that our goal in this example is to elect k=4 committee members. Let's look at this group of voters and observe that these voters form half of the society. Thus, intuitively, they should be able to control half of the committee seats. Namely, they should be able to decide about 2 committee members. However, this group all agrees on some 2 candidates, so it is possible to give each of these voters 2 representatives by selecting only 2 candidates in total. Similarly, we can observe that this group of voters form 1/4 of the society, so they should be able to decide about 1/4 of the committee, that is about 1 candidate. They all agree on at least 1 candidate. Actually, they agree on 2, but agreeing on 1 is sufficient. So on average, those voters should be given at least 1 representative in the elected committee. So the intuition is the following, that whenever we find such an L-cohesive group of voters in this preference profile, then we should require that this group of voters have at least a certain number of representatives in the elected committee. Formally, we say that a group of voters is L-cohesive if it contains at least L times n over k voters who all approve on at least L same candidates. So the intuition is that if we are given n voters and k candidates, then a group of n over k voters should control at least 1 member of the committee. Thus, the group of L times n over k voters should be able to control at least L committee members. Thus, those voters should have on average at least L representatives in the elected committee. For example, here, this group is L-cohesive for L equal 2. Thus, this group should be able to control at least 2 members of the elected committee, and thus get on average at least 2 representatives in the elected committee. This property is very appealing, however, it is also very strong. One can show that there exists no committee election rule that would satisfy this property. Let's look at this following example. Here we have 12 voters and the size of the committee to be elected is 3. We observe that the first 4 voters, they form 1/3 of the society and they all agree on the candidate A. Thus, they should be given at least on average, one representative in the elected committee. This is possible to achieve only if we elect A. By looking at voters V4 up to V7, we infer that candidate B should be selected. By the same argument, by looking at the voters from V7 up to V10, we infer that the candidate C should be selected. And by looking at voters V10 up to V12 plus V1, we also infer that candidate D must be selected. So we see that in order that for our property, in order to be satisfied, we should select A, B, C, and D. However, we can only select 3 candidates, which shows that this property cannot be satisfied by any rule. However, if we slightly relax this property and require that a group of L-cohesive group of voters should be given on average at least L-1 representatives in the elected committee, then this property can be satisfied. And interestingly, PEV is a rule which satisfies this property. Further, if we relax this property even more by requiring that the group of L-cohesive voters should be on average given L-1 divided by 2 committee members, then this property would be satisfied by Phragmén's rule. So these kind of arguments can be interpreted as follows, that PEV is twice more proportional than the Phragmén's rule. Is it really so? Let's have a look at this example and at 2 committees returned by the Phragmén's rule and by PEV. Let's look at the left example, the left committee returned by Phragmén's rule. And here we can see that voters V1, V2, V3 have disjoint preferences from V4, V5, V6. They form half of the society, so intuitively they should be able to control half of the elected candidates. And this is what Phragmén's rule does. The voters V1 up to V3 approve 6 candidates, that is half of the elected candidates. So why PEV behaves differently? So what PEV observes is that by removing one representative of voter V1, that is by removing C4, and by adding one representative for voter V4, for example, C13, then we reduce the societal inequality. That is, we remove one voter, we decrease the number of representatives for one voter from 4 to 3, and at the same time, we increase the number of representatives for one voter from 2 to 3. And the same the same is achieved by removing candidate C5 and adding candidate C14, and by removing C6 and adding C15. So indeed, we can see that PEV implements a type of proportionality which is very concerned about the welfare of the voters, and it's particularly tries to reduce the inequality in the voter satisfaction, which can harm some voters. For example, it harms voters V1, V2, V3 for being agreeable and easy to satisfy. So we can see that in fact, we are dealing here with 2 types of proportionality. One is proportionality which is concerned with welfare, which is implemented by PEV, and one is proportionality which is concerned with the power of the voters, where the emphasis is put on the fact that a group of a certain fraction group of voters should be able to control a certain fraction of committee members. So these 2 ideas are formalized by certain properties, and the properties that formalize the idea of proportionality with respect to welfare, as for PEV, have been extensively studied in the literature. And in this paper, we formulate, we define new 2 properties, and priceability and laminar proportionality, which aim at capturing this other type of proportionality, which is satisfied by Phragmén's rule and which is failed by PEV. So our first property, laminar proportionality, describes how the rule should behave on certain well-behaved profiles. And the second property that we look at is called priceability. Intuitively, priceability requires that a committee elected should be supported by a certain payment system which explains how the voters pay for the candidates that should be elected. So formally, a price system is a pair where the first element of this pair is the global price, that is the total amount of money that needs to be paid for a candidate in order for this candidate to be selected as a committee member. This the second, for each voter, we define a payment function PI, and the payment function must satisfy the following two properties. A voter can only pay for candidates that she approves of, and the voter can spend at most $1 in total for all the candidates that she pays for. We say that the price system supports a committee W if the following hold. For each elected candidate, the sum of the payments to this candidate must equal the price that is needed for this candidate to be selected. No candidate outside of the committee, no candidate which is not elected, can get any payment. And there exist no unelected candidates whose supporters in total have the remaining unspent budget of more than P. Because if such a candidate would exist, then those voters could use their money to buy this additional candidate. If each committee produced by a voting rule satisfies priceability, then we say that a voting rule satisfies priceability. For example, we can see that this committee returned by Phragmén's rule in our previous example is priceable, and the corresponding price system would be the following. We can set the price to P equal half of the dollar, and voter V1 can pay 1/6 for candidates C1, C2, C3, and half of the remaining budget to C4. Similarly, voter V2 can pay 1/6 of the dollar for C1, C2, and C3, and half of the dollar for C5, and so on and so forth. And we can see that indeed, then all the voters, each of the voters will spend at most, actually here, exactly $1, and each elected candidate will get the total payment of half of the dollar. So in this paper, we also have shown that these two properties, laminar proportionality and priceability, are incompatible with the understanding of proportionality, which is welfarist in spirit. We have also proposed a new voting rule, which satisfies laminar proportionality, priceability, and some other desired proportionality-related properties. This rule seems a little bit similar to the Phragmén's rule, but with the tweak that the voters are given their budget upfront rather than they earn it continuously. This voting rule is quite simple and appealing, but due to space constraints, I will not describe it in detail. However, I will quickly show a comparison of the voting rules that we considered in our paper and an overview of the properties that they satisfy. So let me conclude also by giving an interesting open question that we encountered and we do not have an answer for. This open question is the following: does there always exist a Pareto optimal priceable rule? So all rules which satisfy priceability that we know, that is the Phragmén's rule and our new method that we found, that we developed as the part of this project, fail Pareto optimality. So this would be nice to know whether these two properties are incompatible or whether one can find a rule which satisfies both.